Alright guys, so problem I gave you yesterday is a orbital mechanics problem from the 2007 AP test. So I think it's a pretty good representation of what an orbital mechanics problem that you would see would be like. So this is basically just dealing with a planet, talking about Mars, and then a satellite that is going in a circular orbit around it. This problem is pretty straightforward until you get to the last couple parts. So for part A, those of you that did it, that saw it, did well on that. So you're looking for the radius of the satellite's orbit. And since that is circular, then we just look at the circumference of our orbit and divide that by the time. So we have our velocity equals 2 pi r over t. And you're given both velocity and the time in meters per second and seconds respectively. So that's just going to be 3,400 meters per second is equal to 2 pi r divided by 70, 80 seconds. And we just rearrange that problem. So 3,400 times 70, 80, all divided by 2 pi equals r. And if we do that calculation, we get that the radius is about 3.83. If my iPad will work, times 10 to the 6th power, and that's going to be in meters. Apologize for the handwriting, my iPad's glitching out right now. So basic distance over time. And here in this video, I have a tendency to talk kind of quick when I'm dealing with these. So pause it if you need to get the work done right. All right. So our next one is calculate the mass of Mars. So for this problem, we have to use our universal gravitation formula. F equals g times the mass of Mars times the mass of the satellite divided by the radius of the orbit squared. And we know that since this is a circular orbit, that that force of gravity is going to be its centripetal force. And that's going to be the mass of the satellite there. So just looking at this equation here, I can cancel out one of my radiuses. I can cancel out the mass of the satellite. And then I'm left with a new equation, v squared equals g times the mass of Mars divided by the radius. We know v from the problem, we know radius from the last part of the problem. So we just plug in what we know, 3,400 meters per second. That's going to be squared equals g, 6.67 times 10 to the negative 11th. Newton meter squared per kilogram squared. I'm just going to leave these units off because it's a little tough to try on an iPad. Times the mass of Mars, all divided by the radius of the orbit. Which is the 3.83 times 10 to the 6 meters. And if you rearrange this equation, calculate it out, I get the mass of Mars was 6.64 times 10 to the 23rd kilograms. If you look up this value, it is a little different than what the mass of Mars is usually given to you in physics textbooks, and I think that was so that they could see if you were memorizing the mass of Mars from a textbook or if you were actually calculating it. But again, this one right here is a really straightforward problem. Alright, so when we get into part C, this gets where it's a little bit more confusing. So you're talking about, for part C, I asked to calculate the mechanical energy of the scanning satellite in orbit. So mechanical energy, given by the symbol U, is always given to be the potential energy of an object due to gravity, or spring, but this is not a spring problem, plus the kinetic energy of an object. So, kinetic energy is straightforward. We know that kinetic energy is 1/2 mv squared. But potential energy, if you remember from class the other day, is given by the formula that negative g times mass 1 times mass 2 divided by the distance between the two of them. And remember, it's negative because we said that potential energy has to have a zero, and it's measured off that zero. And for gravity, that zero is going to be somewhere that is far away as possible. So this right here is 0 joules at some distance from infinity. So as we get closer to our planet, we get more and more negative. Because you know from class, if you have a higher distance, then you have to get more potential energy. So if 0 is an infinity, then if we get higher, we get larger because less negative is a larger number. So universal gravitation potential energy is negative, and then kinetic energy is just our old trusty 1/2 mv squared. And then we basically plug in everything we have from our numbers earlier. 6.67 times 10 to the negative 11th. We know the mass of Mars from our earlier problem, 6.64 times 10 to the 23rd. And that's going to be a negative number. The mass of the satellite is given to you to be 930 kilograms, all over the radius of the orbit. And then we have this whole thing, kind of put it in blocks if you want to, and we're going to add the 1/2 times the mass, and we're talking about the satellite, so it's just going to be 930 kilograms times the velocity squared. So we have this like great big formula, and if we calculate it out, we get that the kinetic, or the potential energy, is negative 1.075 times 10 to the 10th joules, and the kinetic energy will be a positive 5.375 times 10 to the 9th joules. And if we add those up, our total mechanical energy is negative 5.375 times 10 to the 9th joules. So this is a negative potential energy, which, if you recall me talking in class of the day, is very, very common for objects to have a negative potential energy. We're dealing with like satellites in space or things that are really, really high. And it's negative just because, as again I said earlier, the 0 for potential energy and gravitational objects is at distance infinity, which is really far away. So that was one of the trickier problems in this website. A couple of y'all that I saw turned in work. You had this formula here, but you put a 1/2 out in front of it, and I'm not entirely sure where that came from. I don't know if that was from the notes or if I made a mistake on the board, but just look at it in terms of conservation of energy, and if you set your gravitation negative, then it all works out. All right, so part D is basically just a multiple choice problem. You have your planet, and then you have your original orbit, which is at that 3.83 times 10 to the 6 meters, or something like that. And you're asked that if you were to basically move it into a closer orbit, what would happen to the time? So there's a couple of different ways to do this. The most straightforward way to do this is to look at Kepler's third law. And if you remember, Kepler's third law just says that r cubed over t squared for one object is equal to r cubed over t squared for a second object, as long as the two objects are orbiting the same body. And when we did this derivation in class, we talked about it orbiting the sun, but you could do the same thing here for an object orbiting the moon. And if you just look at basically this proportionality here, then you see it's a fraction. So if the r cubed over t squared must hold constant because it's equal to some constant number, we could calculate if we wanted to. If r goes down, because that's what's happening here, we're talking about a new radius versus our larger radius. So if r goes down, and this fraction is to maintain the same value, then t must also go down. And since t is going down, that means that we have a shorter period. So that is the straightforward way to do it. If you want to do it a different way, you can actually take your whole conservation of energy or your escape velocity formula, that g equals or velocity equals g times the mass of our rotating object divided by the radius, and you can convert that velocity to 2 pi r over t equals g times the mass over r all square root. And you can actually rewrite this, square everything, and get all the t's by themselves, and you'll get that basically t squared equals 4 pi squared r cubed over g times the mass of Mars. And you'll notice that, again, we end up with the same proportionality of this t squared to that r cubed that we dealt with up here. So if this r cubed goes down, then the t squared is going to go down as a result, because everything else right here is going to be constant. I would recommend just doing the straight Kepler-Stokes route, but if you want to take the longer derivation from centripetal force equals force of gravity, you can do that as well. And now the last one, part E. Part E was rather tricky. It looked straightforward to begin with, and I think that everybody that turned it in took the straightforward route, but there's a little hidden trick in there which caused you to miss it, and caused me to miss it as well, because I didn't see the little hidden trick. So it goes, what makes this one a little difficult is that, let's say we have our planet, and we're told that the orbit is actually elliptical, which means that it is I'm going to exaggerate it a little bit, but it looks kind of like egg-shaped a little bit. And you're told that you know the closest distance and you know the farthest distance. And the closest distance is the 3.71 times 10 to the fifth, and the farthest distance is the 4.36 times 10 to the fifth, and that's both in meters. But when we draw this out, one thing that y'all missed, and I understand because I missed as well when I first worked this one out, is that these distances are from the surface and not from the center of the orbit. So what we have to do is take each of these values and we have to add in the radius of Mars, which if you look at the beginning of the problem, that radius of Mars is given to you. So there's a couple of different ways we can do this problem. We can look at conservation of energy and look at the mechanical energy, which is going to be the negative g m1 m2 over r plus 1/2 mv squared for each one. Or we can look at angular momentum. Angular momentum is much more straightforward. So if you remember, angular momentum is I omega. And in this case, we're talking about a planet. Now, a planet is a sphere, but we're talking about the planet as it goes around or talking about the satellite as it goes around our object, not the planet itself. So we can treat that as just a random object. So I is going to be mr squared, where that r is going to be the distance from the center of the object, so we'll have two different r's each time. And omega can be rewritten as the velocity divided by the radius. And what that will do is allow us to kind of cancel out one of these and leave us with that alternate definition of angular momentum, which is just mvr. Now, as we go around this planet, our angular momentum must be conserved. So I can say that L at our closest approach must equal L at our furthest approach, which gives me the formula mass times our velocity when we're close times our radius when we're close is equal to mass times the velocity when we're far times the radius when we're far. And what you'll see here is that the masses immediately cancel out, like that. And we have two velocities and two radiuses. So when we do this, we have to factor in the radius of the planet. So at our closest approach, our velocity is 3,400 meters per second. And our radius will be the distance that we're given, the 3.71 times 10 to the 5th meters. And we got to add in the radius of the planet, the 3.43 times 10 to the 6 meters. And that's going to equal our final velocity times the furthest distance plus, again, the radius of the planet. And then we can do this math in the calculator, you can work it out. But we'll find a new velocity, which is 3,400, excuse me, not 400, 3,343 meters per second, which is really close to our new velocity. But these, the radius here and the radius here are pretty close. This is just a slight elliptical orbit. So that problem was tricky, but if you drew your picture correctly, and I didn't draw a picture to begin with, it kind of made sense, but it's kind of weird wording. So hopefully you got this well, or you did well in this problem, and this right here was informative. So I'll give you another problem later on today, and we'll do this again tomorrow.